All right, so picking up, last time we were talking about sig figs, particularly sig figs in calculations. So these were the last few problems that we worked through. And actually, let me go back and reiterate on these sort of sig figs rules. Where's that table? Here it is. All right, so all non-zero digits are significant. Interior zeros are significant. Leading zeros are never significant. There are very, very few times where I will say something with absolute certainty in chemistry in general, because only the Sith deal in absolutes. But this is one of them. Leading zeros, never significant. Trailing zeros, only if there's a written decimal point. So you get a written decimal point, then you get a trailing zero as being significant. If there's an implied decimal point and trailing zeros, then those are not significant. And at best, it's ambiguous. Now, I know in the pre-lab assignment and in the lab manual, it says if there are trailing zeros in this kind of situation, then you only count the non-zero numbers. So this would be 1 sig fig according to the lab manual. This would be 1 sig fig according to the manual. This would be 4. So if you did that for that pre-lab assignment, I'll say that's okay. Yeah?
I could be wrong, but can we also write those in scientific notation if we want to like imply that like there is a decimal then?
You can't. If I gave you this number and I said, okay, how many sig figs is that? You can't tell because you don't know how many of the zeros are significant.
Right.
So if it's a number given to you, you can't do that because you don't know how many are actually significant. If you do a calculation and it spits out a really large number and you're going to have trailing zeros, then you have to write it in scientific notation to accurately show how many sig figs there are. No. Okay, so sig figs go hand in hand then with this next section, which is precision and accuracy. And we're going to be talking about this. I mean, this is most of what the lab is today. So accuracy refers to how close the measured value is to the actual value. So for any measurement, how close is it to the actual? And then precision is how close a series of measurements are to one another. So precision and accuracy are not necessarily related. You could have a very accurate measurement, but it could be very imprecise. And actually these 3 students here, all right, 3 students who repeatedly weighed a lead block known to have a true mass of 10 grams. So because we know what the true mass is, we can determine if their measurements are accurate. And by looking at the grouping of their measurements, we can determine if they are precise. So if they're close together, they're precise. If they're close to 10, then they're accurate. And a better way than just looking at numbers is actually to put them in a bar chart like this. Gives you a better idea of the distribution of those numbers. So for example, for student A, we would say that they are inaccurate and imprecise because their average measurement is 10.3 grams. We know it's supposed to be 10, so they weren't close to that. And they were imprecise. Their first measurement's 10.49. Their second measurement was 9.79, 2 numbers that are really far apart. Third is 9.92 and 10.31. So their numbers are all over the place. Who knows what they're doing every time they take this lead weight off the scale and put it back on? Something's going wrong there. For student B, the numbers are now much closer together, right? All of those bars are about the same height, but they're all too low. So we would say that student B is precise but inaccurate. Right? They didn't get the correct number, but their numbers were close together. And this is actually one of the things that when I look at lab reports or if I look at calculations, this is the kind of thing that I'm noticing. If you're consistently off, if you're consistently low, that probably means there's a systematic error in whatever you're doing. So you're leaving something out or you're doing something here every single time that's causing your measurement to be low. Student C, however, is both accurate and precise. Their numbers are all really close together, and they're all very close to the true value. And their average comes out to 10.01, right? Pretty much right on the money. So the results of student A are both inaccurate and imprecise, and those are random errors. So a random error is an error that has an equal probability of being too high or too low. Yeah, they're all over the place. The results of student B are precise but inaccurate, which, as I said, is a systematic error, which either tends towards being too high or too low across all the measurements. And then the results of student C display little systematic or random error. They're both accurate and precise. So sometimes you'll get random errors and you can still be accurate and precise because your numbers are close to the true value and they're always going to vary a little bit. If your numbers are coming out exactly the same every single time, I'll be a little bit suspicious. Maybe not on these scales in the lab, but on the analytical balances, they're always just subtle variations. So this is where we're getting into most of the rest of chemistry is going to be unit conversion problems. Other problems will require you to use specific equations, so more than Chem 20. There are specific equations that we have to be using for different calculations. But using units as a guide to solve problems, we can do something called dimensional analysis. And this is one of the most powerful things that you can learn in chemistry, and it applies to some physics as well. Sometimes it's way more abstract in physics. There's, if you took Chem 20, you know R is the gas law constant. That also gets used in Chem 2, but it's in completely different units. But if you dig deep enough to the roots of all of those units, you can tell that it's the same number just using different units, just been converted. So your units, for this reason, should always be included in your calculations. Units can be multiplied or divided and canceled like any other algebraic quantity, so like x in an equation. Right? If we take x times x, you get x squared. Units do the same thing. Okay? Units do the same thing. So if you have centimeters times centimeters, you get centimeters squared, and dividing them as well. So a unit equation is a statement of two equivalent quantities. So here we have 2.54 centimeters equals 1 inch. So if I was to take a ruler, or if you were to take a ruler from the back, I have one up here, you could look at that and you could take two rulers, put them next to each other. Take the centimeter side, put it up next to the inch side of another ruler. If you go to 2.54 centimeters on the metric ruler, it's going to be 1 inch on the English side of the other ruler. Right? Those lengths are the same. And in this way, to get a little bit abstract here, units are names that we use for certain distances or certain masses or certain quantities that we've just all agreed on. So when I say 1 meter, somebody in Japan can take a meter stick and measure out 1 meter, and it's the same distance. So when we're talking about a unit equation like this, we're saying that this distance of 2.54 centimeters is equal to the distance of 1 inch. And we can only do these kinds of unit equations for units that describe the same type of thing. So you can't convert, be careful here because there's some weird ones that you can do. You can't convert a unit of length into mass. I couldn't say that 2 feet is equal to 1 pound. It doesn't make any sense. How is a distance and a mass equal? Now there's some weird ones, right? If you take centimeters and you do centimeters, this is slightly an example of something else. All right, centimeters, if we take centimeters cubed, we can say that 1 centimeter cubed is equal to 1 milliliter. Because by cubing centimeters, we're describing, I wish I'd brought those 3D printed cubes now, we're describing a volume. And so because that description of a volume, 1 centimeter cubed, is equal to 1 milliliter, now we've kind of like, in a sense, gone from length to volume. But to do the example that I have here, right, we can take this unit equation and use it to convert between units. So let's say we've got 3 feet. If we want to convert 3 inches. 3 inches and we want to convert that into centimeters, we take our unit equation and we write it as a fraction. And the way that we write that fraction is going to depend on what we're trying to convert. So in this case, we want to cancel out the units of inches. So we put the 1 inch on the bottom, 2.54 centimeters on top. And when we multiply 3 inches by this quantity, we'll get, without canceling anything out yet, where's my calculator? And this is where we're treating these units like algebraic quantities. So this is 7.62 inches times centimeters divided by inches. So now we've got inches divided by inches. Those cancel out, just like x divided by x would. And so we're left with 7.62 centimeters. And then the reason we can flip this conversion factor here one way or the other is because the length, the physical length that each of those terms describes is the same. So it's essentially 1. And so we could rewrite this and we can convert our 7.62 centimeters back into inches by using the inverse conversion factor. And the sooner that you learn how to manipulate units like this, the better you're going to be in chemistry, because that is most of it. So most of our conversions will follow this same form. There are a few rare ones that we'll talk about where you're converting units in the numerator and the denominator. But for example, here, if we have a given unit, that's what's given in our problem. So we have 12 inches. And now we want to convert that into centimeters. We're again using this same conversion factor of 2.54 centimeters equals 1 inch. And so we'll put match the given unit, I should say, in the denominator of our conversion factor. 2.54 centimeters is the desired unit in the numerator. And that'll give us 12 times 2.54, 30.48 centimeters, because the units of inches will cancel. So what would my answer be with the correct number of sig figs? 3.0 times 10 to the 1?
I meant 2 sig figs.
I figured that. Or I guess we could in this case say 30 decimal. It just always feels weird to do that. I prefer this in situations of trailing zeros, even if the trailing zeros match the number of sig figs. Correct number of sig figs? Was there something else? Oh yeah, and just again, we talked a little bit about conversion factors, right? Meter or a metric to metric is always going to be exact, and then English to English is always exact. One of the few exact conversion factors between the two is inches to centimeters. That is, the inch is defined as 2.54 centimeters. All right, yeah.
On like quizzes and tests, do you want us to memorize these conversion factors, or are we going to have some sort of?
I will. Okay, so for the metric conversion factors, I do want you to memorize. So that's those prefixes, metric prefixes, and there are again a few to start with, like kilo, milli. Those are really the big ones. For English to metric ones, I will give you those if they're needed.
So like kilograms to pounds and stuff like that?
Yeah.
Okay.
Yep.
Thank you.
Eventually you get a sense for those, like it's like about 2.2 pounds per kilogram. Right, so the general problem solving strategy then for like any, especially word problems, right, that's constantly a pain point, or word problems, is you identify first your starting point. That's your given information. Well, write down your given numbers with their units, any per units, so something like miles per hour. Struggling to think of another one. Like grams per milliliter. Those per units might be used as conversion factors, kind of more often than not they are. I've struggled to find a way to sort of formally state how to identify if something is a starting point, especially when it involves per units. Most of the time, it's not going to be, if you can use it as a conversion factor, it's likely that it's not going to be your starting number, but you'll use it as part of the problem. And the next part is to identify the endpoint, which is what you have to find. And then probably the trickiest part is devise a way to get from the starting point to the end point, or a conceptual plan. And you might have to look up conversion factors. On an exam, again, memorize the metric conversion factors, prefix conversion factors. But I'll give you other ones that you might need. And then solve. So you follow your plan, use a calculator to do all your calculations, make sure you write out all of your units, and then do it twice. If you want to be really sure that you're doing everything correctly, make sure you do it twice. Because sometimes you might make a mistake. Forget a decimal, write in an extra digit, that kind of thing. And then check, like, does your answer make sense? Are the units correct? That's probably the hardest one to learn because you have to have some familiarity with the units. But if you're thinking about a problem, it needs to make sense also from a conceptual standpoint. And that's the other hard part about chemistry, is that most of the problems have that conceptual backbone that guides your problem solving. Okay, so I want to convert from 288 centimeters to yards. So what's our given? 288 centimeters. This is an easy one in terms of what the given is, right? We're only given one number. If you don't have a quantity of something, then you can't use it as a starting number because there's nowhere to go from not knowing what it is. And then we want to calculate what? What do we want to find? Yards. All right. So the more that you can kind of view these problems like a puzzle, the better. So there's a chain of conversions that will get us from centimeters to yards. Sometimes it's one step, sometimes it's two, sometimes it's a bunch more. You'll learn pretty quickly that my extra credit problems on exams are basically just insane conversion problems, some of them at least. So we're starting at 288 centimeters. What's going to get us closer to finding yards? Inches. Yeah. So what's that conversion factor going to look like?
2.54 centimeters to 1 inch.
All right, so do I put the 2.54 centimeters on top or bottom? Bottom. And then 1 inch on top. Okay, so we're now in units of inches. So we want to go from inches to yards. I think there's two ways we could do this.
36 inches in a yard.
Yeah, so we could either go from inches to feet, so 12 inches in a foot, and then go from feet to yards. Or we could jump straight from inches to yards because we know there's 3 feet in a yard. Let's do that because it's going to be shorter. So 36 inches. 1 yard. And then with these unit conversion problems like this, once the units in your last conversion, the units on top match what you're trying to find, then you're done. Now you plug it into your calculator. And I like to say you multiply across the top, divide by the bottom. So we got 288. We can ignore these ones, right? Because multiplying by 1 is just going to be itself. So when you type this into your calculator, depending on what your division looks like, it should be 288 divided by 2.54 divided by 36. And how many sig figs should we have?
Would it be 3? Because
36 to 1 is exact, and 2.54 centimeters to 1 inch is also exact. So it's whatever we started with. So it'll be 3.15 yards. Okay. Let's, we'll leave this one. So this is an example where I'm going to leave this one. So if you want to circle it on your sheet with all the problems on it, we'll come back and this will be one to work on. It'll take like 10 minutes to go back and do some of these. This is 43, we're on 44 then. So conversion factors, Oh, yeah. Conversion factors for metric prefixes, these are the ones that I want you to memorize. The metric prefix tells you what the conversion factor is going to be. So especially for a base unit and the same type of unit with a prefix, so we're talking like kilometers to meters here, a kilometer, 1 kilometer means 1,000 meters. So that kilo means 1,000. So this is 1,000 meters. And that's an exact conversion, right? Metric to metric. So prefix goes on one side and the multiplier on the other side. They never go together. Once you're more comfortable with these, they can be written differently. But this is the easiest way to do it, is if you always make sure that this multiplier, this 1,000, or whatever it happens to be for whatever metric conversion you're doing, always goes with the base unit. So if both units have prefixes, unless you're real confident, use 2 steps instead. So go from one prefix to the base unit and then to the other prefix unit. So an example of that, if we want to go from centimeters to nanometers, those are both in meters, but they both have prefixes. So we'd go from centimeters to meters and then to nanometers. And then just to show you what those conversion factors would look like, so let's just say it's 1 centimeter. Actually, let me pick a different number. Let's do 3 centimeters. So 3 centimeters, if we want to go from centimeters to meters, then this is going to be 100 centimeters is equal to 1 meter. Oh wait, did I actually just do the thing that I said to never do? Yeah, the prefix goes on one side and the multiplier on the other. This is an example of 2 ways you could do this. But a centimeter is 1/100th of a meter. So this would be 1 times 10 to the negative 2 meters equals 1 centimeter. And then if we want to go from meters to nanometers, then 1 nanometer. Does anybody know what a nano? -9. Because remember, nano is 9, because they both start with n. So this is 1 times 10 to the negative 9 meters. All right, so the multiplier is going with that base unit, because the prefixes are descriptions of these other units relative to the base unit. If you are way more, it's one of those things, if you're comfortable with it, this is not the only way. This is just if you're uncomfortable with metric prefixes, this is the most surefire way to not get your prefixes and multipliers backwards. Okay, so let's do one of these. So if we want to convert from 0.00432 liters to milliliters, what's our starting value? Yep. And then what's the conversion factor from liters to milliliters? Huh? Yeah.
So it'd be milliliters on top, liters on bottom, maybe 0.001.
Oh yeah, you could write it like that.
Or I mean 10 to the negative.
10 to the negative 3.
Yeah.
So this is going to be 4.23 milliliters.
I did it differently, but I still have the answer. I put,
1,000 milliliters.
yeah.
Yeah, so, right. And this is where like your level of familiarity with these units comes into play. Because you could write this as 1,000 milliliters over 1 liter, and you're still going to get the same answer. Huh?
You can also move the decimal point.
Yeah, for especially milli or kilo, you're just moving it by a factor of 1,000, 3 places. If you get the right answer, and I go back and I look at your math and it makes sense, that's fine. I'm just saying, yeah, like if you are comfortable with 1,000 milliliters as 1 liter, and you never screw it up, you never get it backwards, then that's fine. You do you. Like there are multiple ways to do a lot of things in chemistry, which is part of the difficulty, part of the confusion. If you struggle with these prefixes, then keeping the multiplier with the base unit, I think, can help. Kind of gives it
You
a,
get them switched up, then as long as you know that milliliters is less than liters, then you should.
Yeah.
Yeah, but then again, it comes back down to a familiarity with like, oh yeah, milliliter is small, a liter is large.
It's like completely opposite.
Yeah, like a liter of soda is like this big. A milliliter of soda is like this much. So, right, and that's also getting back to that tip of like, make sure it makes sense. If we do this backwards, then this many liters would be times 10 to the negative 5 milliliters, which is even smaller. Okay, and we'll come back for 46. Units raised to a power. This is one that's kind of tricky sometimes. So when building conversion factors for units raised to a power, raise both the number and the unit to the power. And the thing that always gets missed is raising the number along with the unit to that power. So for example, we can do centimeters to inches again. But if we want to do centimeters squared, right, talking about an area, then it'll be inches squared, and we square both of these. So this is 2.54 squared, and the centimeters are squared. So we get 6.45 centimeters squared equals 1 inch squared. And just, I don't know, if this clicks, it clicks. If it doesn't, it doesn't. But when you're doing this kind of thing, let's say that this is, right, that's 2.54 centimeters. When you're making it, when you're squaring it, you're literally making a square. So that's like this, and then we've got a square where this side is 2.54 centimeters. And then the area contained inside of that, those sort of two lines making that square, is going to be 6.45 centimeters squared. And when you take this to the next sort of dimension, then you're saying now we take the square and we make it 2.54 centimeters high, and that's 2.54 centimeters cubed. And these are still equal to each other. Right, so one divided by the other. We're now just describing an area. And so each side of this would be 1 inch, and this side would be 1 inch. And so they're an equivalent area. All right, so on the practical side, we wanted to know how many cubic centimeters are there in 2.11 yards cubed. So what's our starting? 2.11 yards cubed, or cubic yards. And then we want to get to centimeters cubed. So 2.11 yards cubed. How do we get over to centimeters cubed?
Turn yards into feet, feet and inches into centimeters.
Yeah. Yeah, we could do that. So if we go to, and so like last time I made this jump, instead of going from yards to feet, I went yards to inches, but let's do yards to feet this time. And the trick to this is correctly applying the cube to everything. So if we want to go from yards to feet, what's the conversion from yards to feet? Not yards cubed, not feet cubed, yards to feet.
3 feet per yard.
3 feet per yard. Whoops. So 3 feet, 1 yard, and now because we're doing this cubed, cube that whole thing. So that means it's going to be 9 feet cubed per 1 yard cubed. And then if we want to go from feet to inches, all right, 1 foot, 12 inches, and again, have to cube that whole conversion factor. And then if we want to go from inches to centimeters, same thing, or at least the same sort of pattern. That 1 inch is 2.54 centimeters, then cube the whole thing. And now the units here, once cubed, will match the units here. So then on your calculator, it'll be, again, multiply across the top, divide by everything on the bottom, 2.11 times 3 cubed times 12 cubed times 2.54. Oops. And again, there are more than one ways to do this also. That is a very large number. There we go. 1 point. How many sig figs should this have? 3. All of those cubes don't change anything because those are all exact conversions. So 1.61 times 10 to the 6 centimeters cubed. Right? Yeah, look at that. Any questions? Cubed units? We'll leave that one to come back to it. Oh, I thought I put those somewhere else. Okay, so density is a conversion factor. So, wait, did we talk about density yet? Wait a second. I think we did, right? I mentioned that it was an intrinsic property.
Yeah.
Okay. So my practice problems, I guess I put them back here because we're talking about conversions. Right, so density is an intrinsic property of things, so we can use it to convert between the volume of something to the mass of something, or vice versa. Right, let me flip back. Okay, so density is a conversion factor. Yeah, we'll do one of these. Backpackers often use canisters of white gas to fuel a cooking stove's burner. If one canister contains 1.45 liters of white gas and the density of the gas is 0.710 grams per centimeter cubed, what is the mass of the fuel in kilograms? So what's our starting value for this? 1.45 liters. All right, and we want to convert that into kilograms by the end. Yeah. We got to do some stuff in between. So knowing that we're given this 0.71 grams per centimeter cubed, that's a hint as to where we need to start converting units. Because this gives us the relationship between a mass and a volume, right? Because we can't convert otherwise units of volume into mass, or units of length into something else. So how do we get from liters to centimeters cubed?
Centimeters cubed equals milliliters, so we can go to milliliters.
Yep, so we go to milliliters here. I'm going to continue to follow the conventions that I laid out earlier. So 1 times 10 to the negative 3 liters is 1 milliliter. And so then we can go from milliliters into, and this is probably one to memorize. So 1 milliliter is equal to 1 centimeter cubed. That's a defined quantity. And then from centimeters cubed, now we have, or now we can use our density that we were given. And that'll take us from centimeters cubed into grams. So this is 0.710 grams per 1 centimeter cubed. All right, so how do we go from grams to kilograms? Yeah. So this is not even the way that I normally do this. So this is going to be grams is 1 times 10 to the 3 grams is 1 kilogram. So 1.45 times 0.710, and then divide by 1e to the negative 3, divided by 1e to the 3. Oh, there's another trick we could have done here. How many sig figs? Yeah. So this would be 1.03 kilograms.
So you have done 1 times 10 to the negative 3 kilograms is 1 gram.
The multiplier and the prefix never go together.
Okay.
So the multiplier is always on the base unit. Yeah. Maybe I'll do a survey about that. Because for some of those, yeah, do it one way or do it the other way. Okay. All right, so problems involving an equation. So we'll come back to 51. I'll give you guys some time. Yeah, I think we're just going to have to push the lectures back by half. Because we're not going to finish this and then have time to do anything with the next section because it's almost, well, it's 6 o'clock right now. So to give you guys some time. What? Oh.
So is that from what time the lab started?
Oh yeah, 6:30. So we got till 6:20 for this, in theory. The lab tonight is short, so we could go over, but it's not enough to be worth it, I don't think. we'll be fine. There's a makeup day. So I will adjust the reading. That's really what I wanted to avoid, is having to adjust all those reading quizzes. It's a lot. It's a lot of questions to move around. All right, so problems involving an equation. So I think these are what most people actually like the most, is if there's an equation, then you can figure out what numbers need to go into the equation and then solve for whatever variable ends up being left over. So these are different than the other conversions that we've been talking about using unit analysis. Sometimes you have to do the two together. But the equation will be a relationship between given quantities and defined quantity, or the quantity that you're looking for. One of those is going to be temperature conversions. I will give you these equations for the temperature conversion. Well, I'll give you the equation for Celsius to Fahrenheit. I do expect you to memorize the Celsius to Kelvin. So 273.15 plus Celsius gives you Kelvin. And these are done with formulas because there's some kind of weird stuff going on. Part of that is because Celsius and Fahrenheit scales differ in the size of their degrees. So like 1 degree Celsius is larger than 1 degree Fahrenheit. All right, so gallium. Gallium's a really cool metal. It's a solid metal at room temperature, but it'll melt it to liquid in your hand. The melting point of gallium is 85.6 degrees Fahrenheit. What is the temperature on the Celsius scale and on the Kelvin scale? So I always have to look this one up. So if we've got 85.6 degrees Fahrenheit, then we'd say, okay, degrees C is equal to degrees Fahrenheit minus 32 divided by 1.8. If it helps, the reason that you subtract by 32 is because 0 Fahrenheit is, 32 degrees Fahrenheit is 0 Celsius. Right? So the freezing point of water is kind of where those are each set. So Fahrenheit minus 32 moves the starting point so the zeros line up. And then dividing by 1.8 changes the size of the Fahrenheit sort of size interval. So just plug and chug. 85.6 degrees Fahrenheit minus 32 divided by 1.8 equals degrees C. And notice that there's not anything going on with units here. This is a different kind of mathematical transformation. You can't just use unit analysis to get from one to the other. So let's see, I got 29.8 degrees Celsius. And I guess I should write this, 29.77 repeating. Yeah, the sig figs here are going to end up being whatever it is in the initial. So whatever number goes in, keep that same number of sig figs. These are, like the 32 and the 1.8 are integral to the formula. There's part of the formula, those are exact. The reason that I wanted to write this in here, so this is the number you would report. You'd say A is this. Going on to the next step, you should use the 29.777 repeating. So for B, we want to find the temperature in the Kelvin scale. So that'll be, write the equation, K equals degrees C plus 273.15. So this will be 29.77 repeating. So this would be 292.77 repeating. Oh, I forgot my decimal. And again, well, actually, this one is not quite exact. So actually, I need to look this up if the 273.15 is exact. It's based on whatever absolute zero is, and so it's going to depend on how well we know absolute zero. 302.93 Kelvin. So it'll be B. And for Kelvin, it's not degrees Kelvin, it's just Kelvin. That's the unit. Okay, let's see. Do you want to do one of these? Yeah, let's do one more of these because it's a different type of problem with an equation. So this one says find the radius of an aluminum cylinder that is 2 centimeters long and has a mass of 12.4 grams. For cylinder, V equals pi r squared times the length. So this is one where we really want to write out all of the givens. So we got 2.00 centimeters equals L, 12.4 grams. That equals a mass. We don't have a mass in this equation, but we are given the density, which is 2.70 grams per centimeter cubed. So looking at our equation, V equals pi r squared times L, the length. Which quantities can we fill in here right now? Yeah, so we've got L. We want to find R. That's what we're looking for. Pi is a number. So how do we get the volume of the cylinder?
Use the grams and the density.
Yeah, use the grams and the density. Right? Density allows us to convert. So start with the 12.4 grams. And then we want to cancel out grams and get units of volume, or centimeters cubed. So it's going to be 2.70 grams per 1 centimeter cubed. So 12.4 divided by 2.7. That is going to be 4.259 centimeters cubed. I know the rule of thumb that I gave you, I think, was at least 5 or 2 more past whatever's supposed to be significant. Sometimes I just go until I don't have to. Well, I'll go up to 2, and then if I have to round up, then I'll add the next digit so that I'm rounding down. Again, keeping it in your calculator is the best way to do it. Right, so this is now the volume. So that equals V. So you can type in our 4.59259 centimeters cubed equals pi times r squared times our length, which is 2 centimeters. And in an equation like this, there's not a constant with units here, but since this is in centimeters, we want to make sure that our centimeters cubed is also in centimeters. All right, so if this volume was given in grams, or the density was given in grams per milliliter, you'd want to convert that into centimeters cubed so it matches the units in the rest of the problem. Another hint at the units that you want to use is that we're looking for the radius, which is going to be a length. All right, so now we just need to rearrange this. So we're going to get centimeters cubed divided by pi times 2 centimeters equals r squared. And then because I'm very bad at keeping track of how much space I have, go over this way, and it'll be 4.59259 centimeters cubed divided by pi times 2 centimeters, and that's all the square root of that to get r. You could also take the original expression, rearrange it for r before you plug in any numbers. It's usually cleaner. All right, so now 4.59, oh wait, I have the whole thing in my calculator. So divided by pi divided by 2, and then square root of all that. So r equals 0. Checking for sig figs, 3 sig figs. 4.9 centimeters is r. And actually, there's a weird thing that happens when you take the square root for significant figures. But, so that's kind of a weird algebra-heavy problem. Any questions on that one? If your calculator has a pi button, use the pi button. Or This was a chant that my dad taught me. Sine, sine, cosine, sine, 3.14159. That's pi to whatever many digits that is. Okay? Nice. All right. So then the rest of these, in the 8 minutes that we have left, I mean, you can keep on working on these up until we start lab, and even into lab a little bit. And I will answer questions if you have them. But we will be pushing things back a little bit. So the stuff that we were supposed to get to today now gets pushed back to Wednesday, and the stuff that we were supposed to do on Wednesday gets pushed back to the following Monday, so on and so forth down the line. But there is one day before the first exam where we have makeup time for that. So.